All right, so we're going to do a couple of the homework problems. I think that'll meet the bill for what we're trying to do. So this is, you might recognize this is homework problem 3 from homework 7, I believe. So you got a wall here, got a beam coming out of that wall. It's tied up here by a rope. There's some tension force associated with that. There's some weight hung from the middle of the beam here. And again, it's fixed to this wall at A. Here are all your dimensions. I'll give you a second to look at those. Maybe copy them down. Okay. So if you look at this blue section right here, broken it out here as well with some cross-sectional dimensions for the beam itself. It differs a little bit from problem 3 in that I've changed the 3 points of interest. Got one that's sitting on the center line of the beam, one that's 2 inches above that, and the last one's 2 inches above that at the top of the beam. So you got a point of interest at the center, point of interest 2 inches above that, so just between the top and the middle of the beam, and then one at the top of the beam. We want to find the maximum shear stress at all 3 of those points. And we also want to find the deflection and slope of the beam at this cross section, which for reference again is right here. Okay, I got some specifications for the loads, and we're off to the races. So I just kind of threw down the free body diagram for this. You all did a pretty good job with this if I remember correctly. So I'm not going to spend too much time on it. Essentially, the fixed boundary condition is a reaction force in each direction as well as a reaction moment. The tension is just force at some angle, which you have to figure out. That's all this stuff. And you have a weight hanging from the center of the beam. That's Fe. So if I resolve this tension force into components, just as you did on the homework, it's just T cosine hin theta and T sine theta. In this case, Ty is T sine theta, Tx would just be T cosine theta. So that's pretty straightforward. Next question though is, okay, where do I go from here? Because our objective, in order to get over to these guys, we need to, in order to find stress at these guys, we need to find what the bending moment is going across the beam, as well as what the shear force is going across the beam. So we have to find out what these guys are. So let's rock and roll. So if I'm looking at, say, a summation of forces, let's do summation of forces in the x direction because that's going to be simple. It's going to be Tx is going to the left, so it's negative according to my sign convention here. Tx is going to the left, Fax going to the right. So by definition, those guys are going to be equal and opposite. Great. Now I can start on the rest of it. Now, smartest thing is probably going to be to do a summation of forces in the y direction. Actually, it probably doesn't matter. So I got Fay going vertically, Fe is going down, then Ty is going up. Ma is just a moment, so there we go. All right, so I can just solve for Fay directly. Ty minus Fe. If I do the math for that guy, let's see, Tay is 2.4 kips, Fe is 3.5 kips, means that I'm looking at negative 0.9 kips. For Fay. So I've drawn it pointing upwards, it's actually directed downwards. Oh, sorry, negative 1.1 kips. And it's directed downwards because it came out negative in the summation of forces. Okay, to get that reaction moment, do a summation of moments. Let's do it at A. Okay, so we'll sum moments around A here. The forces at A do not create a moment around A because they are there. The moment arm is 0. The moment at A certainly produces a moment around A. That reaction moment, MMA, because it's not a force, it's a moment. FE should label these things. Sorry, I'm being a terrible example. 3 foot there, and then AB equals 6 feet because I don't have enough space to draw in the lines. So FE is making a negative moment around A. TY is the tension's making a positive moment around A. So minus FE times, let's see, it would be AE or 3 feet, plus TY times AB or 6 feet. A equals 0. So if I wanted to solve for MA, B, TY, AB sorry, that's A minus, that's a plus, FE times AE, substitute into that, gets me negative 1 kip times 6 foot plus 3.5 kips times 3 foot and that is 3.53 times minus 6. So that's a 4.5 kip foot moment. And I notice that my cross-section dimensions are all in inches, and usually stresses are in PSI or pounds per square inch. So I'm just going to convert this into kip inches right now. So that's 54 kip inches. Great. All right, so those are all my reaction moments and forces. Okay, so next thing, shear and bending moment diagrams. Now that I know all my forces and moments, now I have to do something with them. So if I look at my free body diagram, it looks like I'm going to have 2 different sections to take here because two areas where my forces are going to be different, kind of divided by FE in the middle. So if I take my first section, say from the wall, and I go out, shear force, bending moment, I have all my stuff at the wall here, so FAY, make sure everything's drawn exactly the same as they did it originally so I don't have to change anything. And there's MA. Great. Okay, so if I do a summation of, oh, and I guess there has to be a reaction force in the x direction here because I have a non-zero FAX. So if we look at this, this is going to have to do my summation force in the y. So FAY is going in the positive direction. Shear force is going in the negative direction. That's all my forces. Where shear force is the same as FAY, which is negative 1.1 kip. Summation forces in the x is also straightforward. Just have FAX, RX So therefore, the horizontal reaction force equal to FAX, which is equal to 2.4 kips. Great. Fun one's the summation of moments. Remember, we always take around the section. So got my bending moment at the section. I have this MA over here, so that's a moment. It's in the positive direction. And I got FAY, which is making a moment of FAY, negative FAY, times X around the section. Okay, so if I solve this guy out, MB equals FAY X minus MA. Okay, and the fact that I don't have any numbers in this is fine. I expect my moment to be, my bending moment to be a function of X, because how far I am from a wall or a force matters. So this is okay. If I wanted to throw some numbers in, it would be something like FAY is negative 1.1 kip times X minus 54 kip inches. Okay. So next section. So shear force, bending moment, Rx. I can still see my wall because I started there. So there's all my reactions from there. Then I'm also including that vertical force in the middle of the beam. I'm still going to measure X from the far left-hand side just for consistency's sake. And I know that FE is at some distance 3 foot or 36 inches from the wall. Because I used inches in one place, I want to use them everywhere now. So just so I'm consistent and I don't get screwed up by units. So just call that AE for shorthand. All right, so where to go from here? Same gig as last time. So summation of forces in the Y. Got FAY. Make sure I got some positive directions here. That would help me out. FAY minus FE minus V equals 0. So my shear force equals FAY minus FE. Or if you worked out the math for that one, FAY is negative 1.1 kips. And FE is 3.5 kip. Subtract those, get negative 4.6 kips. Okay, great. All right, summation of forces in the X. Still straightforward. FAX minus RX equals 0. Therefore, RX equals FAX. That's 2.4 kip. Okay. Excuse me. Okay, and then the fun one. Summation of moments. Again, about the section. So, let's see, you got MA, still a positive moment over here. MB, also still a positive moment over there. FE is making some moment around the section. So the moment arm is that long, right? From FE to the section. That distance is going to be X minus AE, or if I measure X from over here, that's that whole distance, the whole distance of the beam from the left-hand side to the section. So I need to subtract out the 3 foot from A to E if I want the distance from E to the section. So let's create a positive moment. So FE times X minus AE. And then I have FAY, make it a negative moment, X away from the section. So there we go. All right, I'm solving for bending moment. So MB, so that's what? FAY X minus FE X minus AE minus MA. If I rearrange this puppy a little bit, I can say something like FAY minus FE times X takes care of those two terms. Sorry, those two terms. Then minus MA plus FEAE. So I got kind of my constant over here and my slope over here if I was thinking about this like a line. All right, and if I wanted to throw numbers at that, it might look something like this. So FAY is what, negative 1.1 kips. FE is 3.5, so subtract those, get my negative 4.6 kip times X. And FE, again, is 3.5. A is 3 feet or 36 inches. So that's 126 kip inches. We said that MA is 54 kip inches. So if I can fit it in here, I can rewrite this as negative 4.6 kip times X, or plus rather, 72 kip inches. All right, so that's my bending moment in the second half there. And just for kicks and giggles, if I put 3 foot or 36 inches into both of these, they should be the same. So let's just do a test here. Let's find out what they are at x equals 36. So this one would be, what, 36, 1.1 times, then 54. So this gets us negative 93.6 kip inches. This one down here, it's what, 36.6 negative times, then 72 plus, also gets us negative 93.6 kip inches. So both this expression and this expression come up with the same bending moment at the point that they intersect, which would be here at E, which is 36 inches from the wall. You use 36 inches because my moments are all in kip inches now, so just to be consistent in my units. So cool. So these bending moment equations are consistent, so I have some confidence that they are correct. Okay, so now that I have those, I can start figuring out stresses. Let's do that because that was our first objective there. So if I look at this particular section, let's find bending moment and shear stress there, shear force there. So pop back. So I don't need that equation because that's not for the right part of the beam. If I go over to this guy, this is for the right part of the beam. Looking at x equals 12 inches. our section is 12 inches from the wall, which is where I'm measuring X from. So let's see, my shear force is not going to change. So at the section of interest, so the one that was blue originally, shear force is negative 1.1 kip. Bending moment, let's see, it's Fayx minus MA. So MB at X equals 12 inches. So I'm finding the bending moment when X equals 12 inches. So that would be like negative 1.1 kip times 12 inches minus 54 kip inches. So if we work that one out, it's like negative 67.2 kip inches. Awesome. All right. So that gives me a bending moment. So if I wanted to find shear stress and bending stress now, it'd be fairly straightforward. Let's start with bending stress. So we know that bending stress is a form of normal stress distributed across a cross section, depending on where you are on the cross section. So if I redrew my thing here, so this is a 6-inch by 8-inch section. It's a rectangle, so I know that the neutral axis is dead in the middle because that's where the centroid is. And I'm interested in finding stress at 3 points. Let's call one of them's right in the center, one of them's between the top and the center, the other one's at the top. So I want to find stress at those 3 points. So that's 2 inches up. And the last one's 2 inches above that. Okay. And by definition, that's my y direction. All right. Cool. So I know that, so this is my second moment of area, right? Or my cross-sectional moment of inertia, depending on where you look for it. Of area. Okay. So for a rectangle, that's 1/12 BH cubed, where H, the cubed term, is the one that's kind of in the direction of the bending. In this case, we know that we're bending kind of in that direction around this axis. So like that, if you will. So my 8 inches is the cubed one. So goes my bending moment. My second moment of area. So 6 inches, 8 inches cubed. And then my y is whatever point I want to look at. So obviously on the axis here, we'll call these, let's see, A, B, C, D, E, F. We'll call these F, G, and H. So obviously it's at F, the normal stress is going to be 0 because y equals 0. At sigma g, it's going to be non-zero. So we have to figure that one out. So y is 2 inches there. So if I punch that one in, let's see. 1/12, 6, there's an 8. Hang on. Okay, cool. 8 cubed is 512 times 6 times 12th. Just write myself a note that this is 256 inches to the fourth. Okay. Okay, so that times y sigma g. Remember, we have kips up here. So this is negative 0.525 KSI, because we never dropped that 1,000, that order of that, which is called 1,000 pounds there. And then at H, it's same gig, except Y is now 4 inches. So it's negative 1.05 KSI. All right, cool. So, got some negative numbers. That's kind of interesting. Note these are all solely from bending. We haven't talked about the other normal force sets in there. One thing at a time. Okay, so I got some negative signs in here, so you have to figure out what the crap those mean. So if you look back at this guy, we know that if I support a beam on two ends and I pull down in the middle, the beam is going to bend something like this. So I'm holding this end, going here to kind of pull down in the middle. It's going to bend something like that. Yeah. So we know that this beam is going to be bending something like there. Okay. So question is, where am I at on this beam? Meaning, if I have a negative bending stress, does that mean that I'm in compression up here? Or am I just upside down in general? What's happening? So normally, we could just like reason it out, but now we have like this weird extra curve thing because the wall's fixed right here. So let's see if we can't figure this puppy out. So if I look at if I looked at how I how do I say this? If I looked at how I derived bending stress in the first place, y was always y was towards the positive y direction was originally towards the outside of the curve. So if I have in this case, I'm assuming that up is towards the outside of my curve, and I'm getting this negative stress, which is kind of interesting. And it's because I have this negative bending moment. So in my derivation, I had positive bending moment. Y was towards the outside of the curve. So in this case, when I'm going up, I know that I'm not going towards the outside of the curve. I'm going towards the inside of the curve instead, because my bending moment is negative. So that means that this is in fact a compressive stress. Okay, so this puts the beam into compression. So when I go to look at my section, so there's my section. Ooh. And I can draw my bending stress on it. I also have to take into account the fact that I have a normal stress there. So remember, if I go back to my thing I have an Rx. So I have some uniformly distributed compressive stress there because Rx is a compressive force. So get this guy just by Rx over A. So that's what sigma equals Rx over A. That equals 2.4 kips over an area of 6 inches times 8 inches for 48 inches square, which gets me 0.05 KSI. Okay, so when I go to find stress at points F, G, and H, I'm going to have to take into account this extra compressive stress too. So if I come back here, I can say that the total combined normal stress at FG and HR at F, the bending stress was 0, so that's from bending. And this is compressive, so it has to be negative. And I'll add the compressive stress to that, so it's going to be negative 0.05 KSI, or negative 50 PSI. At G, from bending is negative 0.525 KSI minus the uniform compressive stress, that's negative 0.05 KSI. So that's what, negative 0.575 KSI. And at sigma H, looking at negative 1.05 KSI minus 0.05 KSI. That's what, negative 1.1 KSI. Cool. All right, so those are our total combined normal stresses in the x direction. Cool. All right, so that's part of the answer. But we also need to find what stress that shear force creates. We said the shear force at the section is negative 1.1 kip. Great. All right. So that means that if we look at expression for shear stress, it's what VQ for IT. We know that second moment of area, before we figured out it's 256 inches to the fourth. Thickness of the thing is constant. The whole beam is 6 inches across. V, we just have there. Q is the only thing that we have to ponder about a little bit. So Q, for a rectangular cross section, we said was 1/2 the width of the cross section. In this case, it's 6 inches wide. And then that multiplied by the half height of the cross section squared minus y squared. So the total cross section is 8 inches tall, so half that's 4 inches squared, and then we pick a point to find stress at. So if we work this puppy out, Let's see, 1.1 minus, I got 6 inches, 256 inches to the fourth. So it's like negative 0.002148. Let's see, inches cubed. Fourth, okay. Yeah, so this is, so units of this puppy are kip per inch to the fourth multiplied by 4 inches squared minus y squared. Okay, so if I look at the top of the beam, obviously at h, tau xy at h is going to be 0, because y will be 4 inches, so that'll be 0. Tau xy at point G, that's 2 inches up, so y is 2 inches, so that's what? 16 minus 4 is 12. So that gives us negative 0.0258 KSI. And shear stress at F, y is 0 at that point, is 16 times that gives us negative 0.0344 KSI. Great. So that gives us our shear stress. So we have shear stress and normal stress at a point. We should be able to figure out our maximum shear stress, which maximum shear stress, which, as before we said, is just the radius of Moore's circle, or oops, out here, or just sigma x minus sigma y over 2 squared plus tau xy squared. Great. All right, in this case, we didn't have any sigma y, because that would mean that we have forces compressing the beam or pulling the beam apart, go in the y direction. We don't have that, so that's 0. So I can just take all my normal stresses, divide by 2, square them, and add them to corresponding shear stresses. So one at a time, it looks something like this. So this would be tau xy max at F, let's say. So this would be the center of the beam. So it would be, let's see, negative 50 psi over 2 squared plus, this is at F, so 34.4 psi negative squared, all that to the 1/2 power. So that gets me what? Let's see, 25 squared, 34.4 squared, add this together and square root it. Gets me 42.5 psi at the center. So that's maximum shear stress at F. Do the same thing for each of the other two. So let's see, G, it's negative 575 psi for 2 squared plus 25.8 psi negative squared, all that to the 1/2 power. So 575 for 2 squared, 25.8 squared at those, square root. Oops, typed that wrong. 575 over 2, 25.8 8. 8 square. That should get us like 288.7 psi. So that's maximum shear stress at point G. Then this is H. Okay. So H is negative 1.1 KSI over 2 squared plus 0 square rooted. So essentially it's just 1.1 over 2 or 550 psi. That's maximum shear stress at that top point. All right, so that's that. Okay, so that's part 1. Now we just have to find deflection and slope of the beam at that same point. So we know that second derivative y with respect to x is m over EI. If I know E, I sub it in. I know it's 256 inches to the fourth. For kicks and giggles, let's say that this thing is A36 structural steel, so I can go to the back of the book and say that modulus of elasticity is 29 MSI, or 29,000 KSI. Great. Now I just have to know the bending moment at the section, which conveniently I've already found. That bending moment, fortunately I did not write it down. That's quite unfortunate. All right, well, oh no, I did write it down. It's but I know MB at the section equals negative 67.2 kip inches. But I need to derive my expression first. So take the integral of these guys, dy dx equals MB x. Well, actually, in this case, sorry, I have an expression for this. Don't I? Bending moment is FAYX minus MA. So this is FAYX squared over 2 minus MAX all over EI plus C1. Since we measured in this section, if I go back to it, x is measured from the left-hand side at x equals 0. We know that both the deflection is 0 and the slope is 0 because it is a fixed boundary. So both those are 0. So x equals 0, dy dx equals 0, therefore C1 equals 0. Great. So integrate again. I get y equals FA yx cubed over 6 minus MA x squared over 2 over EI plus another C. Again, I know at x equals 0, y equals 0 for this beam, because again, fixed to the left-hand side where I measure x from. Therefore, C2 equals 0. So I'm left with y equals FAY x cubed over 6 minus ma x squared over 2, 1 over ei. So if I wanted to find and dy dx equals fay x squared over 2 is max 1 over ei. So if I wanted to find the slope or deflection at x, I just substitute that in, solve it out, and get something that looks vaguely like this. So let's see, it's x equals 12 inches. Let's see, y equals fay is, if I remember correctly, negative 1.1 kips. So negative 1.1, 12 to the third power times that, divide by 6, be like negative 316.8. Then I get, that's kip inches cubed, so I'm not dropping things. MA is negative 54, is 54 kip inches, so 54 times 144 over 2, so 3,888 kip inches times 1 over 29,000 KSI times 256 inches to the fourth, which is 1.347 times 10 to the negative 7th. Okay, so 316.8, 3888 minus times equals negative 0.000566 inches. Deflection of that at that point, and the slope is approximately, by the same token, see 1.1 kips over 2, 144 times. Then we have 54 kip inches times 12. Track those. Is negative 9.795 times 10 to the negative 5th radians. There we go. And that's it. That's problem 1. I'll be right back with problem 2.